Alrighty, folks. So here we go on to lesson 2 of Unit 2, where we're going to be talking now about factoring those polynomial functions. This is why we were kind of looking at dividing polynomials by polynomials in the previous lesson. It was kind of leading us towards this, to being able to actually factor those polynomial functions. As we know, dividing and factoring, they kind of are closely related. Dividing, multiplying, and factoring all kind of interrelated with each other. But before we jump in, as always, take a look at the big ideas for this lesson. These are the main skills and the main questions we're hoping to answer by the end of this lesson, so you can use it as a little check-in for yourself. And if there's anything that's given you trouble on that list, don't be shy to reach out to me with questions or concerns, or maybe you just need to go find more practice for it. But whatever it is, that's the list of stuff that we're hoping to be able to do and answer by the end of this lesson. Okay, let's get started. So to start out here, we're going to just remind ourselves of the x-intercepts and the role that they often play in finding the solution to an equation. Often when we want to find the solution to an equation, we can make use of the x-intercepts of an associated function. That's often a good strategy. It's one we used in Math 10C and one we used in Math 20-1. So don't forget, what is the x-intercept? It's just where the graph crosses the x-axis, right? Hence the name x-intercept. It intercepts with the x-axis. Now, since y equals 0 at the x-axis, we therefore, what we can do is we can take an associated function and figure out, if we had an equation like this, for example, 0 equals 3x minus 6, we can think about the x-intercepts of this graph, y equals 3x minus 6, and if we find the x-intercepts, what we're doing is finding the solution to this equation, because the x-intercepts are just the values of x that would make y equal 0, right? To solve an equation means to find the values of x that make the equation true. So if we took this equation, 0 equals 3x minus 6, and we wanted to solve it, one way we could do that is to find the x-intercepts of y equals 3x minus 6, because those are the values of x that will make y 0, and therefore make this equation here be satisfied. So again, to find the x-intercepts, what we need to do is determine the values of x that make y equals 0 in the function. Okay, that will tell us its x-intercepts. We often call these the zeros of the function because they make the function f of x, or y, they make it equal 0, right? Remember, the value of the function really means the value of y. The output of the function is 0. For the 0 of the function, the output, the y's, is 0. So in Math 10C, we learned how to do this for linear equations, right? Degree of 1, the greatest exponent on x was 1. So for example, if we wanted to find the x-intercept of the line y equals 3x minus 6, we would just solve this equation, right? We would just solve this equation for x. And it's not too bad. If 0 equals 3x minus 6, well, undoing the operations that are happening to x, right? It's being multiplied by 3. It's having 6 subtracted from it. So in order to isolate x, we need to undo those operations. So we could add 6 to both sides to undo the subtraction. 6 equals 3x. And now x is being multiplied by 3, so to undo that, the inverse operation of multiplication is division. So divide both sides by 3. That will cancel out the 3 there and just leave us with x, and we can see that 6 over 3 is 2. Sorry, ran out of room there. So x equals 2. That would be the x-intercept of this equation, right? So our x-intercept is at 2, 0. That's where it crosses the x-axis, because at the x-axis, again, y is 0. All right, and then in Math 20, we just took it a step further. We learned how to solve for the x-intercepts, or the zeros, of quadratic functions. So now the degree of x wasn't 1, it was 2. The highest power on x was 2 now. So for example, if we wanted to find the x-intercepts for y equals x squared plus 4x minus 5, we would solve this equation. 0 equals x squared plus 4x minus 5, right? Can you see how figuring out what x's make this equation true is just finding the x-intercept of this function here? right? If y is equal to x squared plus 4x minus 5, then if we can figure out where x squared plus 4x minus 5 equals 0, then we're finding out where y is 0 for this function, right? 0 is in y's spot here, essentially. So if we can find the values of x that make this true, we're just finding the x-intercepts of this function. And this was super handy when solving quadratic equations, right? Bringing everything to one side and then solving for the value of x that made the equation true was how we solved like 99% of the quadratic equations that we solved in Math 20. But there's a problem here, right? If you're noticing, how are you going to get x isolated, right? How are you going to solve for x? Because I mean, you could subtract 4x from both sides, but then you've still got an x squared. It's not like you can combine these two terms. They're not like. One is an x squared, one is just an x term, so they can't be combined. You could actually do algebra on this all day long, and you'll never be able to just isolate and get it so that it says x equals stuff, right? And solve for what x would be. Unlike with linear equations where that's what we did. So these could not be solved by simply isolating x, like in a linear function, because x often appeared twice with different exponents, like we just saw there. However, the key to solving these was factoring. Hey, what's today's lesson called? Factoring polynomial functions. You can probably see where we're headed with this. We did linear functions in Math 10, quadratic in Math 20, and then in yesterday's lesson, we talked about how we're going to look at polynomial functions up to degree 5. Well, now we're going to look at factoring those functions the same way we did in Math 10 and Math 20 to solve equations or to find x-intercepts or whatever our purpose might be. So factoring made it possible to algebraically determine the x-intercepts of these quadratic functions. Let's remind ourselves of how we did that before we take it and apply it now to new types of functions, higher degree functions. So remember, what is factoring? What is factoring? It's essentially taking an expression and figuring out what would have been multiplied together in order to give that expression, right? And then rewriting it as a product of those factors. For a very simple example, right? Let's factor 6. 6, we ask ourselves, what could we multiply together to make 6? And then can we rewrite it as those things being multiplied together? 6 could be factored and rewritten as 2 times 3, or 1 times 6. Those are both ways we could factor 6, right? Factoring, it's sort of like unmultiplying an expression. It's taking 6 and saying, what are its factors? Well, we could write 6 as 2 times 3. This is still equivalent. Notice, like 2 times 3 is 6. It's not like we've changed what this means. We've just kind of, factored it. We've broken it up into the 2, or at least 2 of the ways that we could things we could multiply together to make 6. Now, why does this make it simple to determine the x-intercepts? Well, once we factored something, we just have 2 things being multiplied together. Okay, the reason factoring made it simple to determine the x-intercepts for a quadratic function, and therefore often to solve a quadratic equation, because if you can make your equation look like this and then factor this side, you're pretty close to solving for what x's make that equation true. In other words, the solutions to the equation. Okay, but once that was factored, you would just have 2 expressions multiplied together being equal to 0. The only way we can multiply 2 numbers together and get an answer of 0 is if one of those numbers is 0, right? If I tell you that m times n equals 0, for example, what do you know about m or n? Well, one or both of them has to be 0, right? There is only 2 ways to make this equation true. If m is 0 or if n is 0, right? If these are anything other than 0, then how can multiplying them together equal 0, right? It's not really possible, okay? So that's the fact that allowed us to solve equations like the example we were just talking about. Let's remind ourselves, how did we do it back in Math 20? Well, we learned a few methods for factoring, but looking at this one, it's a trinomial with a leading coefficient, an a value we would have said in Math 20 of 1, right? ax squared plus bx plus c. So we can actually just use good old product sum method. I say Math 20, but we also did this in Math 10, factoring trinomials, okay? So I'll remind you, we need to ask ourselves what 2 numbers multiplied to the constant, or c, and add to the x coefficient, or the b term, right? So we need to ask ourselves what 2 numbers multiply to -5 and add to +4. And so we can kind of sit there and think about it for a second. Two numbers that multiply to -5, add to +4. When in doubt, you can always just start factoring this out, right? Like 1 and 5. Ooh, 1 and 5 could work if one of them's negative, right? In fact, 1 and 5 are the only factors of this. So yeah, I think it's actually going to be if we do +5 and -1, those will work. And so our factors then, because we found that 5 and -1 would multiply to -5 and they would add to 4, we can write this as 0 equals x plus 5, +5, times x minus 1, -1. So see what I mean? We've factored it. We've said what two things could we multiply together to get this, and this is the result. This has been factored. Could check our work if you're not quite sure, like, how does that equal that? Look, x plus 5 times x minus 1. If I FOIL this out, so to speak, x times x is x squared, x times -1 is -x, 5 times x is 5x, and 5 times -1 is -5. Simplifying that out, x squared, -x plus 5x is 4x, and minus 5. So x squared plus 4x minus 5. Sure enough, it is equivalent, right? If I reverse my factoring by multiplying them back together, I get back to where I started. So again, this is equivalent to this, right? This is just saying you could write x squared plus 4x minus 5, but you could rewrite that as x plus 5 times x minus 1. Now, why is that so powerful? Well, I don't know about you, but I have no idea what number x could be here, right? If I said to you, what number squared plus 4 times that number minus 5 equals 0, you'd probably go, I don't know. And I would agree with you. I don't really know either off the top of my head. But if I told you that two numbers are being multiplied together and the answer is 0, what do we know about the two numbers? You'd be able to figure out, well, they just have to be 0, right? So this equation can be true in two ways. We're multiplying x plus 5 by x minus 1, and the answer is 0. Well, that could be true if x plus 5 is 0, and therefore if x is -5. So there's one solution, right? If x were -5, I'd have 0 times doesn't matter, it would equal 0. -5 would make this equation true. But there's another way to make this equation true. There's another solution. If x minus 1 were to equal 0, because then I would have, doesn't matter, times 0. 1 minus 1 would be 0. So if x were 1, that equation would also be true, and we would have a solution. Okay, so there's just a brief, reminder of what we did with factoring, why factoring was closely related to the x-intercepts and the zeros, or at least why it was so handy for finding them, and therefore the solutions to many quadratic equations. Okay, so all we're doing now, we're taking that same way of thinking, that same concept, and we're going to extend it beyond just quadratics. We're going to go above a degree of 2. Okay, we're going to do it to cubics and quartics and quintics. So in this lesson, our goal is to take what we did in Math 20-1 and extend it beyond just quadratic functions. We want to factor polynomials with a higher degree than 2 to determine their x-intercepts. And again, that can be very helpful for solving problems or equations, including a lot of real-life applications. So today's lesson is going to be it's going to seem a little like disjointed at first. We need a few tools to help us along the way. So it's kind of broken up. We're gonna learn a few concepts and tools that I promise eventually at the end they all come together with the big goal of allowing us to factor polynomial expressions, but we kind of have to build them up as we go. We're gonna put a few ideas into a procedure and then we'll use that procedure, put it all together to actually factor polynomials. So the first stop along the way is the remainder theorem. All right, so this is the first one of those tools I was mentioning that we're going to need to have in our kit to be able to eventually factor polynomials that are of a degree greater than 2, okay? The remainder theorem. So the remainder theorem, you can tell it's got something to do with remainders. In the previous lesson, we talked about dividing polynomials, right? We used two strategies. One was long division, one was synthetic division. To be honest, we mostly use synthetic division. You can use long division if you prefer it. Most people prefer synthetic. It's just a little quicker and easier, okay? Maybe not easier, but quicker, okay? So when we took a polynomial, p of x, and divided it by a binomial that was in the form x minus a, right? That's just standing in for any binomial. We have an x minus some constant. There was often a remainder r. So for example, this is actually the exact lesson we did, or example we did in the previous lesson. We divided x squared plus 4x plus 5 by x plus 1, right? We did it two different ways. Long division like this. We did all the steps of long division, found that our remainder was 2, and we knew the remainder was 2 because there was nothing left to do, right? We divided, multiplied, subtract, and brought down, and we did that and did that and did that. And then eventually we hit the point here where there's a 2, and we can't divide the, oh, there should be an x there. I'm just noticing. Don't know why that's missing. 2 couldn't really be divided by x, so that's our remainder. There's nothing left to bring down. Synthetic division, same idea. We bring down the 1, multiply by -1, add them up, multiply that by the -1, add them up, and then we get to the end. There's nothing left to do, and we're left with this 2, so our remainder is 2. Writing that out as a division statement, we have the dividend divided by the divisor is equal to our quotient. So the result was x plus 3. No matter which method we use, we get that the result is x plus 3. And then plus the remainder over the divisor, right? So our remainder here is 2, okay? Now, that is a great way to find the remainder. You could do the whole thing, but there's actually a faster way that takes advantage of well, some stuff I'll prove to you in a second here, okay? Something called the remainder. The remainder theorem. If all we want to do is find the remainder, right? Yes, we could do the whole thing and find the remainder, but if we don't actually care what the quotient is just yet, and we just want to know what the remainder of that division is going to be, we can use something called the remainder theorem. All it does is provide a quick way to determine the remainder. It's not going to tell you the quotient, but it can tell you what the remainder will be when you do the division. When any polynomial p of x is divided by any binomial in the form x minus a. And here it is. It's pretty simple. It's pretty straightforward. Whenever a polynomial p of x is divided by a binomial x minus a, the remainder is always just going to be p of a. In other words, the remainder will always be just what happens if you put in this number, whatever number you see there, a, into the original polynomial function as x. That's always going to give us the remainder. Now, I get that seems like, what? Like, that's a little bit of a magic trick, isn't it? We can actually kind of prove this. I'll try to do that here for you. I'll try to prove it to you. So I won't do it for every single degree polynomial, but like for a cubic, for example, right? You can try it out for yourself if you're not sure. Try it for a quartic or a quadratic or a quintic function, okay? If we have, let's say we want to do this division. Now notice I'm just putting in general numbers. So B, C, D, E, and A could represent any integer, any number at all that we want. This is how we often like prove that things should always work in math. We keep it general. If we can show that this works for these parameters here that stand in for any number, these coefficients, B, let B be any real number, let C be any real number, D and E be any real number, okay? If I can show that this remainder theorem works for that, for this general case, well, then we've shown that it works for any number because B, C, D, E, and A all represented any number. So I'll show you that this works with this cubic function here. I'm going to use synthetic division. So I'm going to keep it general. I'm just going to use this stuff. So for synthetic division, we put our A value, the thing from the binomial, off to the left. And then we just use the coefficients for the dividend, right? So I just do, in this case, my coefficient B, C, D, E. And again, B, C, D, and E could represent anything. So if we end up showing that we just end up with P of A here, then we can be pretty confident that it would work for any number. Ooh, sorry, cough came out of nowhere. Okay, so let's try doing our synthetic division here with these general terms put in. So we'll bring down the B, okay, then we'll multiply by the A, so that's going to give us AB. Then we're going to add those, so C plus AB. And I'm just realizing now I definitely need to give myself some more room. Okay, now I'll multiply again. So I'm going to do A times C plus AB. What's that going to give me? It's going to give me AC plus A squared B. Okay, and then we're going to add those. So that's going to give me AC plus A squared B plus A, whoops, sorry, no, just plus D. Right, just adding down the columns there. Okay, and now I'm going to multiply this whole thing by A. So what's that going to give me? Well, A times AC is A squared C. A times A squared B is A cubed B. And A times D is AD. And then the last step here, I'm just going to add those all up again. So I'm going to add E to this thing. I'm just going to rewrite it. I don't know why I didn't do this the first time, but I'm going to have A cubed B plus A squared C plus AD, and then I'm going to add the E plus E. Now notice here, maybe if I rearrange it, it'll be a bit more obvious. A cubed times B is the same as B times A cubed. A squared times C is the same as C times A squared. AD is the same as DA plus E. Do you notice anything? Now remember, for synthetic division, the last thing we have here when we're done and there's nothing left to do, that's our remainder. Okay, now look at the polynomial we started with, what we were dividing something, or what we were going to divide by x minus a, right? Look, we found that the a value that we divided by, here's our polynomial, bx squared plus cx squared plus dx plus e. BA cubed plus CA squared plus DA plus E. Notice this is just what you get if you put A in as X in the original polynomial that we were trying to divide by X minus A, right? That's exactly what the remainder theorem said. If we're going to divide a function P of X by some binomial X minus A, the remainder just ends up being the result of putting A into that polynomial in the first place. And we just found that that worked. And remember, B, C, D, and E could have stood in for any number. We were keeping it general so that we could show ourselves that it actually does work for any number, right? If it works for these, and these could represent anything, well, then it should work for anything. Okay, now you could do it for yourself if you're not quite convinced. Try it out for a quadratic. Use the synthetic division there. See if you can prove it for quadratics and for quartics, okay? But all this means, and we've just kind of proven it, is that if you plug the value of a into the polynomial function p of x and then evaluate, the result of that is always just going to give you the remainder. So let's test it out using the example above. What does the remainder theorem give as the remainder of our division? X squared plus 4x plus 5 divided by x plus 1. Well, we know that the remainder should be 2, so let's see if the remainder theorem tells us that, right? We did the whole division and found the remainder was 2. Will the remainder theorem be a faster way to get the same result? Let's see. So for our x minus a, it's x plus 1, so be careful. X minus a is always the form of these, right? So what does that mean a is? A must be negative 1, right? For x minus a to equal x plus 1, we need a to be negative 1, right? X minus a, you could think of that as x minus negative 1. So our a is negative 1. Then p of a, using the remainder theorem, right? If we're going to apply the remainder theorem, we need to figure out what p of a is. So if our a is negative 1, we're looking for p of negative 1. And so that just means what it always means, put negative 1 into our function, our p of x here. So this is going to be, it's x squared plus 4x plus 5. So negative 1 squared plus 4 times negative 1 plus 5. And that's going to equal, negative 1 squared is positive 1. 4 times negative 1 is negative 4 plus 5. And hey, look at this. 1 minus 4 is negative 3. Negative 3 plus 5 is 2. So the remainder of this will be 2. So the remainder is 2, right? Which is exactly what we found when we did the whole thing. Will this work to find the remainder? Absolutely. Is this much faster? Absolutely. You might be saying, oh, I don't really care about finding the remainder quickly. You will, because remember, we're building towards factoring polynomials, and one of the important parts of finding a factor is being able to quickly determine the remainder. So this does become, and we'll have to do it like multiple times to test some things. So it's really handy to have a quick way to find remainders, which is exactly what the remainder theorem is. All we need to do to find the remainder of a division like this, wherever we're dividing a polynomial by x minus a, if we put that a into the polynomial function, it will automatically tell us the remainder. Pretty quick and easy way to do it. Let's try out some examples. So it wants us to determine the remainder when this polynomial, 2x cubed minus 4x squared plus x plus 7, is divided by this binomial, x minus 1. So this is our like p of x, right? That's the polynomial dividend, and this is our x minus a, our binomial divisor, okay? So the remainder theorem says it will just be p of a, right? P of a. So for this one, what does that mean? What's our a? Well, our a, if this is x minus a just equals 1. Right? A is 1. X minus a, we have x minus 1. And this is p of x, so we just need to put in 1 as x, right? So our remainder, just using the remainder theorem, will be p of 1. And let's see what p of 1 is. Well, it's 2x cubed, so I'll do 2 times 1 cubed, minus 4x squared, so minus 4 times 1 squared, plus x, so plus 1, plus 7. So p of 1 is going to equal 2 times 1 cubed. Well, 1 cubed is still 1, so 2 times 1. 1 squared is still 1, so 4 times 1, so minus 4, plus 1 plus 7. And so p of 1 is going to equal 2 minus 4 is negative 2, plus 1 is negative 1, plus 7 is positive 6. Positive 6. Okay, so our remainder will be 6. So remainder is 6. Much quicker than actually doing the division, right? I know synthetic division is pretty quick, but this is even faster. All we had to do was put 1 in as our x, and we found the remainder. We don't have the quotient, that's true, but we do still have the remainder. Let's try this next one here. The partial graph of f of x equals x cubed minus 2x plus 6 is shown to the right. So this graph is showing us everywhere where y is equal to the x value cubed minus 2 times the x value plus 6. Use it to determine the remainder of x cubed minus 2x plus 6 over x minus 2. So the remainder theorem lets us do this pretty quickly. We're taking a polynomial and dividing it by a binomial divisor. So this is our binomial divisor. This is that x minus a. It's what we're dividing by. So this is x minus a. So what's my a? What's a? It's 2. You got it. X minus 2. If that's x minus a, then a must be 2. And this is our polynomial dividend, right? This is the thing we're dividing. That is p of x. Now again, the remainder theorem tells us that we need to just find p of 2, and that will be our remainder. So how can we find p of 2? I mean, we could put 2 into the function, that's true, but why don't we just use the graph? That'll be even quicker, right? So this is just saying if this is the function, it shows us what f of x is at every x. Find what it is when x is 2. So 1, 2 on the x-axis, and it looks like the value of our function when x is 2 is 10. So p of 2 just equals 10. That's just from the graph. So what's the remainder? 10, right? The remainder theorem tells us that for any division of a polynomial by a binomial x minus a, the remainder will be p of a. So that's what we found. P of 2 gives us that this remainder is 10. Pretty quick. Okay, one more example here, and then you can try one out or try a few out. if the remainder is 3 for x cubed plus 4x squared minus x plus k divided by x minus 1, what is the value of k? All right, so a little bit of thinking going on here, but we can use the remainder theorem because, again, we're just taking some polynomial and we're dividing it by some binomial divisor, x minus a, and it's telling us that the remainder is 3. So what does the remainder theorem tells us? Again, it tells us that the remainder, whenever we do p of x divided by x minus a, the remainder will just be p of a, right? Well, we know that our remainder is 3. And we know that our a is 1. And we know the p of x that we were dividing by x minus 1. So we actually know everything in this equation. Like, we have an equation set up here. The only thing we don't know in that equation is the k. As long as there's an equation where you only don't know one thing, then you're able to solve for that one thing, right? Essentially, what we now know is by the remainder theorem, p of 1 has to equal what? It has to equal 3, right? That's what the remainder theorem says. The remainder 3 will just be p of 1. Put 1 into p of x, and you'll get the remainder, okay? So this is an equation we can solve because what's p of 1? Well, p of x is x cubed plus 4x squared minus x plus k. So p of 1 is just going to be 1 cubed plus 4 times 1 squared minus 1 plus k. And that equals 3. Okay, maybe I'll keep the color coding here. I guess I should have made these red then. They're coming from the x minus a part. Okay, so that's going to give us 1 cubed. I might drop the color coding here because we're starting to mix them together. 1 cubed is 1. 4 times 1 squared is still 4. Minus 1 plus k equals 3. Running out of room. I'm just going to move up here. So let me combine some like terms to simplify a bit. 1 plus 4 is 5. 5 minus 1 is 4. So on the left side, we just have 4 plus k equals 3. And then subtract 4 from both sides. We get k equals negative 1, right? Subtract 4 to isolate k. And there we go. K equals negative 1. That's the value of k, right? So we just took advantage of the remainder theorem there. If the remainder is 3, then that means p of a is 3. Well, we know p of x, and we know a is 1. So put 1 into this and figure out what k would need to be in order to make the result be 3. And working it out algebraically, we found that k would have to be negative 1. How could you check your work here? I mean, you could always just take this, actually put in negative 1 as k, and then put your 1 in as x and make sure the result is actually 3, right? Okay, so go ahead and give this one a shot here, which is asking you to use the remainder theorem to determine the remainder for this division. And then you can always take some time to try another couple practice ones before coming back to the video lesson. So pause the video, try it out while it's fresh in your brain, and then we'll move on to the factor theorem. All right, so there is kind of tool 1 that we're going to need, okay, the remainder theorem. We're actually going to kind of combine it with the next one to give us a very powerful tool, but we needed to talk about the remainder theorem before we talk about how it relates to the factor theorem. So the next stop on our little tour of the tools we're going to need is the factor theorem. So don't forget, our ultimate goal today is to be able to factor polynomial functions. We're kind of learning these little skills along the way, but that's why we're learning them, because we're going to use all of them when we actually factor a polynomial, okay? So that we can determine their x-intercepts and or solve equations that involve them. In order to see something, let's just do a little investigation to think about how this connects to factoring. Why are we interested in remainders if we're interested in factoring? Well, what are the factors of 10? What are all the ways you could multiply something to make 10, right? I mean, you could do 1 times 10, 2 times 5, and then you could also make them both negative. Like you could do negative 1 times negative 10 and negative 2 times negative 5. So you could do like plus minus 1, plus minus 2, plus minus 5, plus minus 10, right? Those are all the different things that could be multiplied together as long as you multiply them by the right thing to make 10, right? 1 times 10, or -1 times -10, 2 times 5, or -2 times -5. And that's it. There's no other factors of 10, okay? So with this in mind, let's determine the remainder for some of these divisions and see if we notice anything, right? 10 divided by 1. What's 10 divided by 1? I mean, you could write it out if you want, 1 into 10. I know it's a little painfully obvious, but how many times does 1 go into 10? 10 times. So divide, multiply, so 10 times 1 is 10. 10 minus 10 is 0. Aha, the remainder is 0, right? 10 divided by 1 is 10 with a remainder of 0. So remainder of 0, right? Okay, 10 divided by 2. How many times does 2 go into 10? Well, 5 times. 5 times 2 is 10. 10 minus 10 is 0. And there's nothing left to do, so that's our remainder. Remainder is 0. 10 divided by 3, though, may be a little more interesting. 3. How many times does 3 go into 10? Well, it definitely goes into 10 3 times, right? And 3 times 3 is 9, so that's what's left over. We can fit 3 3s into 10, but that only gives us 9. Now, we can't fit another 3 into 10, otherwise we'd hit 12, and obviously that doesn't fit into 10. So 10 minus 9 is 1, right? And that's our remainder. We have a remainder of 1 here. Because again, 3 does go into 10 3 times, but that only makes 9. So we still have 1 left over to make the 10. So we have a remainder here. Okay, do you notice a pattern? We divided by 1, remainder of 0. Divided by 2, remainder of 0. Let's divide by 4. Notice 4 was not a factor of 10. You can probably see where this is headed, right? How many times does 4 go into 10? Well, twice, not a third time, but it can go twice. 2 times 4 is 8. 10 minus 8 is 2. Nothing left to do, so that's our remainder. The remainder is 2. 4 goes into 10 twice with 2 left over. Okay, so 4, not a factor of 10, and we got a remainder. 10 divided by 5. 5 is a factor of 10. Sure enough, 5 goes into 10 twice with nothing left over, right? Count them out. 5, 10. 2 5s go into 10. So 2 times 5 is 10. And then we'll subtract. Nothing left to do. Our remainder is 0. So notice here, every time we divided by one of these, one of the factors of 10, we got a remainder of 0. Right? The only two where we didn't divide by a factor of 10 are the only two where we got a non-zero remainder. 1 left over, 2 left over. So can you kind of make an observation here, make a rule? What's the remainder when the divisor is a factor of the dividend? It's 0. In other words, there's no remainder. It goes into the divisor, to the dividend evenly, right, with nothing left over. Now, this idea always holds, and honestly, it makes sense. It really makes sense when we think about it. Because what is a factor, or what are factors? They're numbers that we could multiply together to get another number, right? Why are 2 and 5 factors of 10? Because 2 times 5 equals 10, okay? Factors are just numbers or expressions that could be multiplied together to give that expression, right? So naturally, they need to be divisible. Like it's kind of a given consequence of that they're going to be divisible by those expressions. For example, right, since 10 could be rewritten as 2 times 5, that's literally saying that 10 is just 2 5s. So it's not surprising that 10 divided by 2 is just 5, right? If 2 times 5 is 10, then 10 over 2 is 5, with no remainder. Right? Again, if 2 times 3, those are factors of 6, they give us 6, well then it's not surprising that we could write 2 as just 6 divided by 3, right? 6 divided by 3 has no remainder. 6 is just 3 2s. So 6 divided by 3 is just 2. No remainder, okay? If something is a factor, okay, then whatever it's a factor of is by its very nature divisible by it. So this gives us the factor theorem. If x minus a is a factor of a polynomial, p of x, then the remainder of p of x over x minus a is going to be 0. Whenever you divide something by one of its factors, it divides evenly. You're not left with a remainder. So if we combine that knowledge, if we combine the factor theorem with the remainder theorem, what we'll get is basically an even more helpful version of the factor theorem. Remember, the remainder theorem told us that when a polynomial p of x is divided by a binomial x minus a, the remainder is always p of a. To find a factor, what do we want the remainder to be? We want the remainder to be 0 if it's a factor. To find a factor, we want the remainder p of a to be 0. So putting those two ideas together, right, basically putting the remainder theorem into the factor theorem, x minus a is a factor of a polynomial p of x if and only if p of a equals 0, right? This is just saying, from the remainder theorem, it's saying the remainder would be 0. And we know that, sure enough, it's a factor if the remainder, when we divide by it, is 0. So this is just combining the factor theorem with, combining the remainder theorem here with the factor theorem. Let's try out some examples applying the factor theorem. Okay, so it's asking us here, which of the following are factors of p of x equals x cubed minus 7x plus 6? Okay, well, now that we have the factor theorem in our toolkit, this actually becomes a pretty quick question to answer, a pretty easy question to answer. Just put a little reminder here, right? By the factor theorem, we know that any factor, if it's a factor, if x minus a is a factor, then when we put that a into the polynomial, the result should be 0. That's the remainder theorem at work, because this says that's the remainder whenever we divide by x minus a. And the factor theorem tells us the remainder for any division by a factor will be 0. You won't have anything left over because it should divide evenly. So we just need to check if this gives us, if I put the a value into p of x, does it give me 0? If yes, it's a factor. If not, it's not a factor. So let's try this out here. X plus 1, help me out. What is a here? If I divide this by x plus 1, and that's supposed to be x minus a, what's my a? Right, a would be negative 1. So let's find what p of negative 1 is. Just going to do this in black here. I'll drop the color coding. So p of negative 1 is going to be negative 1 cubed minus 7 times negative 1 plus 6. So we really do just need to figure out what this is. P of negative 1 cubed is negative 1, minus 7 times negative 1 is negative 7, plus 6. So p of negative 1 is negative 1 plus 7 plus 6. And that is negative 1 plus 7 is 6. You can already tell this is not going to equal 0, which is really all we're interested in. It ends up equaling 12, right? But all we really wanted to check here just asked us, is it a factor of not or not? And we can see it's not going to equal 0. So p of negative 1 does not equal 0. So x plus 1 is not a factor. Right? If it were a factor, p of a would have equaled 0. X plus 1 must not be a factor because p of negative 1 gave us 12, not 0. A remainder of 12, not a remainder of 0 like we should get for a factor. Okay, next one here. Is x minus 1 a factor of p of x? Well, what's a here? This is x minus a, so my a is just positive 1 in this case, right? X minus a, x minus 1. So what is p of 1? We just have to check if it's 0 or not. So p of 1, 1 cubed minus 7 times 1 plus 6. 1 cubed is 1 minus 7 plus 6. Ooh, I like the look of this. 1 minus 7 plus 6. 1 minus 7 is negative 6 plus 6 is 0. Aha! P of 1 is 0. P of 1 equals 0. P of 1 equals 0, so x minus 1 is a factor. we just found one of the factors of this polynomial, right? You can see why this is super helpful for factoring things. We now know one of the factors. Once we know one factor, it becomes pretty quick to find another factor and then another factor potentially, right? We'll talk about the reasoning behind that as we go and how we can actually use this to find more factors. But you can start to see the groundwork being laid for factoring this completely, right? We just found one of the factors. X minus 1 is a factor of this because P of 1 was 0. Okay, let's try out the factor theorem a couple more times here. X plus 2, help me out. What's A if this is X minus A? Right, A is negative 2 for this, so we need to test negative 2. Put negative 2 into the function and see if the result is 0 or not. So negative 2 cubed minus 7 times negative 2 plus 6. Negative 2 cubed, that's negative 2 times negative 2 times negative 2, which is negative 8. Minus 7 times negative 2, so minus negative 14 plus 6. Now we just got to simplify, so negative 8 plus 14 plus 6. Can already kind of tell, no, this is not going to be a factor. Just to really drive it home, negative 8 plus 14 is 6, and 6 plus 6 is 12. So it equals 12. That tells us the remainder is 12. So is it a factor? No, right? If it were a factor, the remainder should be 0. All factors are evenly divisible by their, all things are evenly divisible by their factors. So this can't be a factor. P of negative 2 does not equal 0. So x plus 2 is not a factor by the factor theorem. Okay, last one here, x minus 2. What's my a for x minus a? I'm dividing by x minus 2. A is positive 2. So to figure out if x minus 2 is a factor, we need to test p of a and see if the remainder is 0. If so, then this must be a factor. So p of 2 is going to be 2 cubed, x cubed, so 2 cubed minus 7 times x, so minus 7 times 2 plus 6. So then p of 2 is just 2 cubed is 8. 7 times 2 is 14 plus 6. Okay, this looks a little more promising because 8 minus 14 is negative 6. Negative 6 plus 6 is 0. So p of 2 is 0. So what does that mean for x minus 2? Is it a factor of this polynomial? You betcha it is. X minus 2 is a factor. Okay, x minus 2 is a factor because p of 2 equaled 0. All right, here's one. If p of 5 is 0, what is one factor of p of x? We don't even have p of x, but we can still answer this question because we'll use the factor theorem, right? Again, p of a is going to tell us the remainder. And they're saying if a is 5, p of 5, the remainder ends up being 0, right? Remainder theorem tells us that p of a is the remainder. Factor theorem tells us that the remainder should be 0 for any factor. So put those together, we now know that if a is 5 in x minus a, the remainder ends up being 0, and therefore that's associated with a factor, right? So if p of a equals 0, then x minus a is a factor of p of x. So what would the x minus a be if p of 5 equals 0 and that's associated with an x minus a? Well, it's 5, right? So x minus 5 must be a factor. Right? Here, our p of a is p of 5. So the x minus a, that is why we're putting in the a there, it's coming from the x minus a. The x minus a must have been x minus 5, to make the input here be 5 and give us that as a 0, right? So our factor, the factor associated with this a value is x minus 5. Alrighty, go ahead and try this one out. It's 2a. Of course, if probably a good time as well to pause and maybe try b, c, d as well. Okay, but at least try this one while it's fresh in your brain. Go ahead, take a second and pause it, check your answer there. And then we'll move on to actually starting to put this stuff together and factoring these polynomial functions fully. Okay, well, not quite yet. We're almost there. We got a couple more things to talk about, but we're getting there. We're getting to the point where we can actually factor these polynomials fully, okay? So remember, again, factoring is simply determining what could be multiplied together to give an expression, and then rewriting that expression as a product of those factors, right? So when we factor a polynomial function, we can then rewrite it as all of its factors multiplied together. We call this factored form. That is what we're building up to, is the factored form of a polynomial function. So for example, if we factored f of x equals x squared plus 4x plus 3, we would find the two factors to be x plus 1 and x plus 3. Again, that comes from our product sum method. We would say what two numbers multiply to 3 and add to 4. By the way, if you're a little rusty on why that's what we ask ourselves and why we can be so sure those are the factors, we can quickly reprove that. If I have two numbers, let's say x plus a, x plus b, where once again, a and b could represent any number at all. So if we can show a pattern or a rule here, we're confident that it works no matter what a and b are. If I multiply this all out, x times x is x squared, x times b is bx, a times x is ax, a times b is ab. And then you can kind of think of those as like terms. How would we combine those like terms? We would just add their coefficients, right? Like if this were a 3x and a 2x, we would add them to get 5x. So we can even do that with the general terms here. This will be, how do I combine those? B plus a x, right? If it was a 3 and a 2, you'd just add them to make 5. It's just a b and an a, so we could say it's b plus a, whatever those are, x plus ab. And that's where that product sum method comes from. Notice, working backwards, if we were started with this and we were asked to factor it, we need to figure out, okay, well, those two numbers would need to multiply to give me this number, this whatever this AB is here, the constant term, and then they would have to add to give me the middle coefficient, right, A plus B. So that's why we can be so sure if we can figure out two numbers that multiply to 3 and add to 4, the two factors will just be x plus one of those times x plus the other, okay? So going back to this one here, two numbers that multiply to 3 and add to 4, how about 1 and 3? That'll do the trick, right? That's where that x plus 1 times x plus 3 came from. That's just an equivalent way of writing the same thing, and you could always check your work by multiplying them back together and making sure you get what you started with. We unmultiplied to factor. If we re-multiply, we should get back to where we began. So therefore, we could write this in its factored form. It's what we just did there. F of x equals x squared plus 4x plus 3 is equivalent to f of x equals x plus 1 times x plus 3. Now remember, if we set f of x equal to 0, y equaling 0, we can solve this factored form quite quickly and easily for the x-intercepts of the function, since y is 0 at the x-intercept. Let's do that. Determine the x-intercepts for the example above. We know that y equals x plus 1 times x plus 3 because we factored it. Well, if we want to know the x-intercepts, we want to know what values of x can make y equal 0. So let's see if we can figure it out. How do we make 0 equal x plus 1 times x plus 3? Well, we're multiplying those two factors together. We are doing x plus 1 times x plus 3. So how do we multiply two numbers together and end up with 0? There's only one way. We have to make one of those numbers be 0. Now there's two ways we could do that here. We could make x equal -1, right? Because if x plus 1 equals 0, then we have 0 times whatever, it's going to equal 0. So how do we make x plus 1 equal 0? We make x equal -1, right? Then we'd have -1 plus 1, which is 0, times -1 plus 3 is 2, but it doesn't matter because 0 times 2 is still 0. Okay, and then there's another way to do it. What could we make x equal here in order to get an overall answer of 0? We could make it -3, right? The other way to make this equation true is to have x plus 3 be 0, and therefore have x be -3. So those are the two solutions to this equation, or the two x-intercepts of this function, okay? And so these ideas give us the following form. This is just for a quadratic, but we could extend this beyond quadratics. Any polynomial function in factored form is just going to have an equation a, that's just some I shouldn't call it a constant, some coefficient that's multiplied by all of this stuff, okay? And then it's just x minus an x-intercept, that's one factor, times x minus another x-intercept, that's another factor. Notice, right? That's all we said here. If -1 is the x-intercept, then this is just written as x minus an x-intercept, x minus -1 times x minus -3, right? All we're saying here is that if we put in the x-intercept, this is going to become 0, and therefore y would equal 0, which is the definition of an x-intercept, the x value that would make y equal 0. So in general, any factored polynomial can be written as a bunch of x minus blank times x minus blank times x minus blank, where the blank tells us about an x-intercept, right? And then this a is just there, again, because technically it's possible for it to be, right? Like it's totally possible that this could have been 2. And does that change my x-intercepts if I throw a 2 in front of there? No, right? Still has an x-intercept of -1, right? This doesn't change the fact that in order to make 2 times something equals 0, one of those somethings needs to be 0, right? This could be 106, and the x-intercepts would still be the same. They'd be at -1 and -3, because multiplying by that 106 isn't going to change the fact that in order to get a y value out of 0, we need to make one of these be 0, right? These are the ones that depend on what x is. And so that value of a in the equation is always just the same a that's the leading coefficient in standard form, which actually makes sense when you think about it, because if you imagine multiplying these all back out together again, right? The highest power of x is just going to come from every time in all of that foiling that you did, every time you were multiplying an x, that leading x by that leading x, right? That would give us x squared. And then eventually we'd have to multiply that x squared by this x to get an x cubed. And if there were more terms, we'd have to multiply that by the x. And the highest power of x just comes from that multiplication over and over again. And then eventually that gets multiplied by our a, giving us a times x to the highest power, right? Which is why that a value that we see kind of out here in the factored form is the same a that's on the leading coefficient in standard form. So if you have something like, ax cubed plus ax squared, not necessarily ax squared, ax cubed plus bx squared plus cx plus d, the factored form is going to look something like a times x minus, I'll just say m times x minus n times x minus p. 3 factors because it's a cubic, right? X times x times x would give us an x cubed, and eventually that x cubed would get multiplied by the a to give us the leading coefficient a. So that's the general kind of how a factored form for a polynomial looks once it's been factored. All right, so they're telling us the x-intercepts here, right? They're telling us in this example that x equaling 2, -2, and 1, that's where we'll find the x-intercepts for this polynomial. And then it wants us to write the polynomial in factored form. Well, telling us the x-intercepts actually kind of tells us the factors, right? There's 3 x-intercepts here. We would expect, 3 factors for a polynomial that's a cubic, because that involves 3 multiplications of an x by an x by an x. So what that's saying, right, if we think about it, is that, again, remember, this means making x equal to -2 or 1 will make p of x equal 0. And so that tells us what some factors are, because it tells us that p of x must look something like an a value. We'll think about the a value in a second, because again, we can't say for sure that, well, here, let me write the factors and then we'll talk about that, okay? if that makes p of x 0, it has to contain a factor like x minus 2. Because then 2 minus 2 would be 0, and I'd have 0. P of x would equal 0. And it has to contain a factor like x plus 2. I got that from the fact that negative 2 was an x-intercept, because that means when I make x negative 2, the polynomial y becomes 0, right? And what's another factor? If 1 is an x-intercept, that tells me that making x 1 can make this function equal 0. So what's another factor we can pick out? X minus 1, right? Notice all I'm using here is the fact that x-intercepts make y equal 0. So if 2 is an x-intercept, that means x minus 2 must have been a factor, because making x2 would make this factor 0. And then I'd have 0 times doesn't matter, it would equal 0. Same thing here. If negative 2 is an x-intercept, making x negative 2 should make this whole thing 0. So that must contain that factor x plus 2. Negative 2 plus 2 would equal 0. It would make the whole right side equal 0, right? Same goes for the 1 there as well. Now, the a is important to think about, because technically, does any of what I just said change if a is 10 or 20 or negative 1,000 or 627? No, right? 627, if I make x 2, 627 times 0 times whatever is still going to equal 0, right? If any of these factors are 0, doesn't matter what a is, the whole right side is still 0, okay? But that a value can take advantage of the fact that the leading coefficient is the same a that we can put in front here in our factored form, okay? Again, because of the fact that if we multiplied this all out, right, we'd end up with eventually an x cubed, and then that x cubed would get multiplied by a. So our polynomial in factored form is just going to be a is, well, our leading coefficient attached to the x cubed is 2. So 2 times x minus 2 times x plus 2 times x minus 1. And there we go. There's that polynomial in factored form. Okay, now you might be saying that, why did we have to learn the other stuff to be able to factor it? That was super quick and easy. Well, they've told us the x-intercepts, right? They're not always going to tell us that. In fact, usually we've got to figure those out on our own. But just getting the idea here of how the x-intercepts and the factored form are very closely related. Because again, the factored form very clearly, easily shows us how to make each factor 0, right? Make x 2, make x negative 2, make x 1. So if that shows us how to make the factor 0, and the factors are all multiplied together to give us y, right? Knowing how to make the factor 0 is how to make the y 0, and therefore how to find the x-intercept, the x's that make y equal 0. Okay. All right, so this one here is interesting. It asks us to use our graphing calculator to factor this polynomial, right? But remember, there's a very close relationship between the factors and the x-intercepts. The x-intercepts kind of tell us the factors, because again, if we can make the factor 0, we make this whole equation 0, therefore we make y 0, and that value of x must be an x-intercept. The value of x that makes y 0 is an x-intercept. So if we can graph this and find the x-intercepts, we can find the factored form of the equation, because each x-intercept will just tell us one of the factors if we know how to interpret it. We can also see here that our leading coefficient is once again 2, so we can get off to a pretty good start here. We know that p of x is going to be a times some factor that we'll get from the x-intercept times another factor that we'll get from the x-intercept, and I'm predicting that there will be 3 factors because x is cubed here. So that involves 3 multiplications of x. So let's go ahead, let's remind ourselves of how to do this on our graphing calculator. I'm going to open up a graphing calculator, I'm going to type in that function, and then we're going to let our calculator tell us the x-intercepts so we can figure out the factors. Okay, so let me just pull up here the calculator. Sorry, I've got to find the equation again. I forget what the equation was. There we go. Okay, so Reminder of how to graph stuff. I mean, I'm sure you've been doing it throughout the course already, but first time it's kind of come up in the notes where we have to use our graphing calculator. So let's go to y equals, that's where we're going to enter our equations. And the equation we wanted to enter was 2x cubed. So I'm going to do 2. Okay, then remember this xt theta n button, that's how we input an x. Y equals 2x cubed. So to put something to the power of 3, well, to put something to the power of anything, we want this button right here. That little almost looks like a hat. Okay. Newer calculators will actually make it look like an exponent. Older calculators just put in that little sign. But that's what I want. I want 2x cubed. Notice my cursor's still up there in the exponent, so I'm just going to hit the right arrow button just to get down out of the exponent. So 2x cubed, subtract. Remember, we want to use that subtract, not this one, not the negative. That'll confuse our calculator. Our calculator, it treats subtract and negative as different things, so it'll be confused if you use that. We want to do the subtract one, that one there. Okay, so 2x cubed minus 5x, and you could do to the power of 2, but there's actually a nice little squared button there, so we can just do minus 5x squared plus x plus 2. That was the equation that we were given in the notes there. So now I want to see the graph of it, so I'm going to hit up here at the top right, graph. Hey, there we go. Now, we might, not on this one, but sometimes you might need to adjust your window settings to be able to see more of the graph or zoom in and see less of the graph, right? Again, window settings, this just means I'll see from negative 10 up to 10 on the x-axis. I'll see from negative 10 up to 10 on the y-axis. That worked out fine here. We can see enough. If we could tell there might be other x-intercepts that we couldn't see, we'd have to zoom out. But this is a cubic. We know the left arm's going down forever, the right arm's going up forever now, so those are all my x-intercepts. So reminder of how to find the x-intercepts. Whenever we're analyzing a graph, like 90% of the functions we want are found in the same place, and that's in second, and then calc or trace. So second, trace, and we want to find, well, the zeros, right? The x-intercepts. We call x-intercepts zeros. That means the same thing because they make the function 0. X-intercepts make the function 0. So again, I just went second trace, then see option 2 there, 0. So I hit 2 for 0. And now I've got a cursor, and do you remember this from Math 20? It's going to say left bound. Do you see that there? What that means is we have to get to the left of the x-intercept we're interested in right now. So first I'm going to find this one right here that my cursor is next to. I need to make sure my cursor is to the left side of it. Essentially what I'm about to do in these next couple steps, I have to sandwich the x-intercept between my cursor. So I'm going to say left bound. I'm now definitely on the left side of that x-intercept. So let me hit enter. Then notice it switches to say right bound. That means get on the right side of that x-intercept. Now, I don't want to go so far that I'm actually to the right of another x-intercept. That can cause confusion for our calculator. It will say, there's 2 x-intercepts in this sandwich that you've made. So I just want to make sure I'm to the right of the x-intercept I'm interested in, but not so far to the right that I actually, have another x-intercept in there. So that looks like a good spot. I'm going to hit enter, and then it says guess. That just says, do you want me to look for an x-intercept? So I'll say enter, yes, and there we go. So our first x-intercept is at negative 0.5 or negative 1/2. So that is one of our, I'm going to list the x-intercepts off to the side. Negative 0.5, I might just say negative 1/2. Kind of nice to work with a fraction in this case. Let's go back to the calculator and find those other ones. So I'm just going to repeat. So second, trace. I want to find a 0. I want to get on the left side of this one now. So enter. And it switches to right bound. Let me get on the right side of it. Looks good there. I'll hit enter. Then it says guess. Hit enter one more time. And there we go. See that? My next x-intercept, it's telling me there that it's when x equals 1. When x equals 1, y equals 0. So let me add that to our list. X equals 1 is an x-intercept. And I see one more x-intercept to find. So let's do that one more time. Second trace. Option 2 to find a 0. Get on the left side of that, but not so far left that I'm on the left of another x-intercept. That looks like a good spot. So enter, right bound, so get on the right side of it. Enter, guess, enter, and there we go. There's the last x-intercept. It's when x is 2. So going back to the notes here, Our three x-intercepts are when x is negative 1/2, 1, and 2. So what are the factors associated with those? Well, x minus 2 would be one of those, right? X minus 2. X minus 1 would be another one. And x plus 1/2. Again, because, let's just write those in. So x plus 1/2, x minus 1, and x plus, minus 2, right? These are the associated factors with those x-intercepts, because if x being negative 1/2 makes the function 0, that tells us it has to contain this factor, x plus 1/2, right? If x is negative 1/2, I have negative 1/2 plus 1/2 is 0, and that would make y 0. And the definition of the x-intercept is the value of x that makes y 0, right? If x were 1, this factor becomes 0, and so y becomes 0. If x were 2, this factor becomes 0, and so y would be 0. So I forgot to actually put in our a there, but let's finish this up. So p of x will equal 2 times x plus 1/2 times x minus 1 times x minus 2. Pretty cool. We just factored that by graphing it. Right? By graphing it to find the x-intercepts and letting the x-intercepts tell us the factor. And then the leading coefficient tells us this leading a here as well. Cool. Alrighty, folks, so here it is for real. The last tool that we're going to kind of need to take with us to be able to fully factor polynomial functions. So we're going to add this tool to our kit, and then we're going to use our entire toolkit of everything we've talked about today to be able to fully factor polynomial functions of degree 3 or greater. Okay? And that is, how do we know where to kind of start looking for factors? So if we consider these following factored equations, they've all just been factored as we would have done in Math 20-1, right? Product sum method for these, decomposition for this one, okay? But they've all been factored, okay? Now, in each case, I want you to compare the constant term to the factors themselves, okay? So what I mean by that is, the factored term in the equation was 6, and then our two factors are x minus 3 and x plus 2, right? 12 is our constant, 3 and 4. 6 is our constant, 2 and 3. Do you notice anything? The zeros, we call those the zeros again, right? The values of x that would make this 0. So that's just my 0, right? The a part in x minus a, they're always factors of the constant term in the unfactored equation, which actually makes a ton of sense, because if you imagine multiplying all the factors back together in order to get back to the original unfactored, like if you wanted to multiply these together to get back to this, right? Where does the constant term come from? It comes from the part of foiling where you multiply this by this. 3 by 2, negative 3 by 2 in this case. So yeah, that constant term just comes from multiplying the two constants in our binomial together. Therefore, these kind of have to be factors of this. We got this by multiplying them together, right? How are we going to get the 12 out? That's going to come from the part of the FOIL where we do 3 times 4, 12. Negative 2 times 3, the negative 6, right? So this constant term is always just going to come from multiplying these two together. In other words, these two are always going to be factors of this, of our constant term. So at some point, all of the constant terms in those factors are multiplied together to give the constant term in the unfactored expression. And this fact, like I said, this gives us the last tool that we'll need to be able to factor any polynomial function. It's something we call the integral zero theorem. Integral meaning integer. So if it has a 0, that's an integer, an x-intercept, that's an integer. Okay, this works well for integers. It kind of falls apart for non-integers, but we don't do it for non-integers. For those, we'd have to do it a little more analytically with, for example, a graphing calculator, but it works very well for integers. So the integral zero theorem is just that. If x minus a is a factor of a polynomial function p of x, then a will be a factor of the constant term of p of x. Now, why is that helpful? Why is it good to know that if we look at the constant term in our polynomial, we know that any factor, the a value here for a binomial factor will have to also, the a value will have to be a factor of that constant term. Why is that so helpful? Well, remember, the factor theorem combined with the remainder theorem, what we were doing earlier in the lesson, lets us very quickly test if a binomial x minus a is a factor of a polynomial function. Okay, now that's great because if we can find a factor, then we can pretty quickly find other factors, right? Once we have one factor, we'll be able to use polynomial division to find the others. I'll talk about that a bit more in a second. But again, if we want to factor something, being able to test if something is a factor is a great start. So the problem we're facing, though, is how do we decide what our a should be? We know how to test if something is a factor, but how do we figure out, like, what somethings to try in the first place? I know how to figure out if x minus a is a factor. I put a into the polynomial function p of x. But how do I know where to start looking for what x minus a could be? You would literally just have to start picking numbers and hope you got lucky before too long, right? That's pretty much where we would be without the integral zero theorem. But with the integral zero theorem, our search for the right a for testing out, is this a factor? Is that a factor? Is this a factor? We can narrow it way down because now we know we only need to test a's that are factors of the constant term in p of x. So all we're going to do is simply look at the constant term of the polynomial we're trying to factor and factor it. The a we need will be one of those factors by the integral zero theorem. Okay, so for example, if you wanted to test for possible zeros, roots, or x-intercepts for y equals x squared minus 10x minus 30, what would we have to try? Well, what is the constant term? It's 30, right? So we know that if some factor, if x minus a is a factor of this, that a is going to have to be a factor of 30. So whatever a is for one factor of this function, whatever that a is, we know it's going to be a factor of 30. So that narrows our search way down. Normally, we just have to start picking numbers and hope we get lucky. But now we can say, okay, whatever that is, if this is a factor, the a is going to be a factor of 30. So we just need to look for factors of 30 as our potential zeros. Right? So what are the factors of 30? Well, you've got 1 and 30, right? 1 and 30. You could do 2 and 15, 3 and 10. I'm just going up in order. I know I'm saying two numbers. I'll do those later. Not 4. 30 isn't divisible by 4, but 5. You could do 5 and 6, right? And now, okay, so 6 times 5, and then our 3 was times 10, and then our 2 was times 15, and our 1 was 30. So I know that looks like a lot. It still looks like a lot, but consider the alternative, right? At least now we know it's going to be one of these numbers. If x minus a is a factor, the a will have to be one of these. There will be multiple factors, okay, but each of them will have an a value that is a factor of 30. This narrows our search way down. It definitely beats just starting at 1 and counting and trying every single number. We've narrowed it a lot down compared to infinite possibilities, okay? Now, again, this is a quadratic, so we probably wouldn't go about it this way. We'd probably just use our Math 20 or Math 10C skills to factor this, but we're going to get into a place where we can't eventually because we're going to be doing cubics and quartics, so that's what we're looking at here. Okay, so this definitely beats random guessing because it narrows our search way down. So now we're ready. You can kind of see the path laid out in front of us, right? This tells us what values of a to check if they're a factor. And then the factor theorem gives us a quick way to check if they actually are a factor or not. So we know we're only going to test these, and we'll use the factor theorem to test them. For example, I'll do p of 1. If p of 1 is 0, I know x minus 1 is a factor. Then I can try p of negative 1 if that doesn't work, and I'll know x plus 1 is a factor if p of negative 1 is 0. So we're going to put this all together now and actually do what we said we were going to do at the beginning. We're going to factor a polynomial with a degree greater than 2. All right, so let's do it. This is kind of a guided example where we're going to go through it step by step, and then eventually we'll just do it all from the beginning by ourselves. But this one's going to walk us through the steps. These are always the steps we're going to follow, okay, in order to factor a polynomial function. But for this first one, they're laid out for us. So it wants us to fully factor x cubed minus 2x squared minus x plus 2. Something we could not do before today using the skills we had from Math 20 and Math 10C. Okay, so this is exciting. So first, it wants us to find the possible factors using the integral zero theorem. Okay, so where do we look for that? How do I figure out what my candidates are for possible zeros? Well, I need to look at the constant term of the polynomial I'm trying to factor. Any zero will be a factor of 2. Now, careful, I didn't say all zeros, or I didn't say all factors of 2 will be zeros. I'm just saying that if it is a zero, it will be a factor of the constant term. So some of the factors of 2 are not going to end up being zeros, but anything that is a zero will be a factor of 2, right? Same thing up here. Not all of these are going to give us factors of this, but any factors of this will be one of these, okay? So let's find the possible factors. We just need to figure out the factors of 2. So factors of 2, well, there's plus or minus 1 and plus or minus 2. There's only 2 factors of 2, 1 and 2. And then you could do -1 times -2 as well. There we go. So that's telling us that the possible factors are, not guaranteed, but the possible factors are x plus 1, x minus 1, x plus 2, or x minus 2, sorry. Those are our possible factors, right? If a is 1, then x minus 1 will be a factor. Okay, if a 0 is -1, then x plus 1 will be a factor. If one of the zeros is 2, x minus 2 will be a factor. If one of the zeros is -2, then x plus 2 will be a factor. And so now what do? We just test them. So the factor theorem tells us, right, we're going to test them using the factor theorem. And the factor theorem combined with the remainder theorem. Okay, so again, just quickly wrote this out here to remind ourselves, right? The factor theorem, if p of x is x cubed minus 2x squared minus x plus 2, the factor theorem says that if x minus a is a factor, then p of that a should equal 0. So we can use that fact to just test each possible a, right? Our possible a's are plus or minus 1 and plus or minus 2. So let's just test those a's out, right? For x plus 1, the a value is -1. For x minus 1, the a value is +1. So we can use the factor theorem to test this out. See if the result when we put in those a's is 0. If so, the associated binomial is a factor of our polynomial. So let's just test them out. You just got to start somewhere. Let's start with 1. Now, word of advice here, folks. Typically, they're nice to you, meaning they'll make it like 1 or -1 or 2 or -2 so that you don't have to test too many of them. So always start with like your 1 and then maybe your -1. And if it's neither of those, you can move on to the 2 or the -2. I recommend always start low so that you don't end up doing more work than you have to. Okay, so let's test a equals 1. What we're really checking here is x minus 1 a factor, right? We're testing to see if x minus a is a factor for when a is 1. Okay, so how do we do that? We find p of a and see if it's equal to 0. So that means for us, we're trying to find p of 1 and see if it's equal to 0. So what's p of 1? P of 1 is x cubed, so 1 cubed, minus 2 times 1 squared, minus x, so minus 1, plus 2. So p of 1 is just going to be 1 cubed is 1, 2 times 1 squared is still 2, minus 1 plus 2. And P of 1 is going to be 1 minus 2 is negative 1, minus 1 is negative 2, plus 2 is 0. Whoa, we got it first try. Now that doesn't always happen. Okay, we'll see examples where it doesn't. Sometimes you test out a equals 1, you find out, oh, it didn't equal 0, so x minus 1 is not a factor. That's okay. We've got 4 to check, so then we would just move on to the next one. But that didn't happen here. We got lucky, right? So when a equals 1, right, think about what we just found. P of a equals 0, right? Compare that to the factor theorem. If x minus a is a factor, then P of a will be 0. We now know that P of 1 is 0, so what does that tell us is a factor? X minus 1. X minus 1 is a factor. Okay, now we know one of the factors. Remember, we're trying to fully factor this, and we just found one of our factors. That's huge. That's a big deal. The next step, what it's going to get us to do is to divide by that factor. I want to go through the logic of that a little bit, okay? Pretend, you're an alien and you've never heard of the number 6. But I told you that one of the factors of 6 is 2. One of the factors of 6 is 2. How could you figure out another factor, right? Remember, we know that a factor means that means I can multiply 2 by something and get an answer of 6, right? 2 is one factor, so there's something I can multiply 2 by and get an answer of 6. How could you figure out that other number? Well, you could take 6 and divide it by 2. Do you see what I'm saying there? If you know one factor, you can divide what you're trying to factor by that factor in order to get the other factor. 2 times something equals 6, so 6 divided by 2 can tell me what that other factor must be, right? Sure enough, 6 divided by 2 is 3, and that tells us, aha, so 2 times 3 equals 6, right? So that's the key takeaway there. If you know one factor of a number or expression, well then divide that number or expression by the one factor you know, and you will automatically be finding another factor. And that's the logic behind this next step here. What we just found was one of the factors of this polynomial. How can we find another factor? We'll take it and divide it by the one factor we found, and that will be guaranteed to give us another factor, right? If you know 2 is a factor of 6, well, divide 6 by 2, and you'll be finding another factor of 6, 3, okay? So that's what we're going to do here. We're going to use, I'll use synthetic. You can use long division if you like, but I'll use synthetic because it's a little quicker to go through, okay? We're going to use synthetic division to divide by the factor we found, because that will give us another factor, right? And that other factor is just going to be the quotient of this division, the result, right? 6 divided by 2 is 3, so if that gives us another factor of 6. Same idea here, but with polynomials. So let's go ahead. We know x minus 1 is a factor. Let's divide our polynomial by x minus 1 to find another factor. So here we go. Let's say we've got x minus 1. Well, we want to divide x cubed minus 2x squared minus x plus 2. We want to divide that by x minus 1, because now we know that x minus 1 is a factor of that. So how would we do that using synthetic division? Let's set it up. So remember, our a value, our potential 0, our 0 in this case, goes here, okay? So what's a here? Again, it's 1, okay? And then for synthetic division, we just use the coefficients of the dividend. So 1x cubed minus 2x squared, so minus 2, minus 1x, so minus 1, plus 2, so a positive 2. Okay, and now I'm just going to go ahead and synthetically divide this to figure out what the other, what the result is when I divide that polynomial by x minus 1. So first things first, you bring this down. So I'm just going to have a 1 here, and then multiply these. 1 times 1 is 1. and then add down the columns. So negative 2 plus 1 is negative 1. And repeat. Multiply 1 by negative 1, that gives me negative 1. Whoops. Negative 1. Add down the columns, so negative 1 plus negative 1 is 0. And then multiply. Oh, sorry, that's not true. You're probably screaming at your computer right there. Negative 1 plus negative 1 is not 0. Negative 1 plus negative 1 is negative 2. Whoopsies. And then 1 times negative 2 is negative 2. And the last step here, we're going to add them. 2 plus negative 2 is 0. Now, is that a good sign or a bad sign that we got 0 as the last step in our synthetic division? Well, do you remember what is the last step of, like, what is this number? The last thing we get in synthetic division. Do you remember what that represents? That's the remainder. So we divided this by a factor of it, and we got a remainder of 0. Hey, we've been talking about that all day today. If something is a remainder, then when you if something is a factor, then when you divide by it, you should have no remainder, right? That's part of the deal for being a factor. It means you evenly go into whatever you're a factor of, right? 6 divided by 2 is 3 with 0 remainder because 2 is a factor of 6, right? So that's good. If we weren't sure that it was a factor before, we're double sure now, okay, that x minus 1 is a factor. So if you did this step correctly, if you did step 1 correctly, and then you divide synthetically correctly, you should always get a remainder of 0. Because after step 1, when we do this part, we should be, if we did it correctly, we should now be dividing by a factor. And dividing by a factor always gives us a remainder of 0. So that's a nice little like checkpoint where you can check your work. Once you do that synthetic division to find the other factor, you better be getting a remainder of 0. If not, maybe go back and check your work, okay? So what is the other factor that this synthetic division has told us? Well, we divided x cubed minus 2x squared minus x plus 2 by x minus 1, and this is the result. So remember, it goes remainder, constant, x term, x squared, x cubed if there was another one, but there's not. So this must just be 1x squared minus x minus 2. That is another factor. So x squared minus x minus 2 is another factor. Okay, and now we just keep going. We keep repeating this process, okay? Typically what we want to do is get it down to a quadratic factor because then we can just do what we did in Math 20 to keep factoring from there. But let's just go ahead and try this out. We're going to rewrite this now. Think about what we've done so far. We've found that p of x, okay, we know that one factor is x minus 1, and we know that the associated factor with that is x squared minus x minus 2, right? Again, you can see the logic here. What did we do when we divided p of x by x minus 1? This is what we got. So imagine dividing both sides by x minus 1. That's how we found this in the first place, okay? So we've found a way to rewrite p of x as a product of two factors, but can we keep going? Can this be factored further? Okay, we've rewritten the polynomial as a product of the two factors we found so far. Can we continue factoring though? Well, in this case, we definitely can, and we could actually just restart this whole process using the quadratic. However, this process, while it's kind of fun, it does take a little bit longer than just using our Math 20 skills because we know how to factor a quadratic very well from Math 20, right? This is just a good old quadratic. We can probably just factor this with product sum method, right? We could use product sum method. So we could ask ourselves, what are two numbers that multiply to negative 2 and add to negative 1? We can think about that for a sec. Multiply to negative 2 and add to 1. Hey, how about negative 2 and positive 1, right? Negative 2 times 1 is negative 2. Negative 2 plus 1 is negative 1. So this should work. So we can now take this and factor that part using our product sum method, kind of just breaking it down even further into its the factors that make it up. So then p of x will equal, here we go, x minus 1. And then here, we've factored this. We now know that this can be written as x minus 2 times x plus 1. X minus 2 times x plus 1. And can we keep going? I don't think so, right? That's about as factored as it gets. But we did it. We factored a cubic. That is p of x written out as a product of its factors. We could check our work if we weren't sure. We could check our work by multiplying it all back out together. So I'll maybe leave that up to you if you want to try doing that. What should happen when we multiply, if we multiply x by x and x by negative 2 and blah, 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 and then whatever that gives us, multiply each term by x plus 1. Well, it should give us what we started with, right? It should give us that x cubed minus 2x squared minus x plus 2. So that would be a quick way to check our work to see if we factored this correctly. Multiply it all back together again. Cool, right? Okay, let's try some more examples. All right, so here's one now. Okay, we're taking off the training wheels. We don't have the steps laid out for us. We're actually just going to do it from the beginning as it would be given to us on, a test or a quiz or a diploma, okay? So it wants us to fully factor this cubic function, okay? I guess it's not a function, it's just an expression. Okay, so I went ahead and wrote out our first step. We're going to figure out what are we testing? What are the possible zeros, right? We don't just want to go on a wild goose chase. Let's narrow it down a bit. So how do I check for those? I look for factors of the constant term, right? So I'm looking for factors of 3 in this case. Well, the factors of 3 is a prime number, so that's nice. It's just 1 and 3. Don't forget, though, the negative option could also give us a 0, right? It could be negative 1 or negative 3. But that makes our search nice and narrow. We just need to test those, right? Any factor of this will just have these as the a value. Any binomial factor will have one of these, not all of them, but one of them as a factor, okay? Or sorry, as the a value. All right. So that was quick. That's step 1. Step 2, we got to test them. Find out, okay, those are the candidates. Those are the possible a values for x minus a being a factor. Now we actually got to figure out which one of them is, or which ones of them, whichever one we find first. So we're now going to test those possible zeros, right? Our possible zeros being 1, -1, 3, -3 with the factor theorem. And don't forget, all the factor theorem says, in combination with the remainder theorem, it says that if x minus a is a factor, then p of a will be 0, because p of a is just the remainder. And for any factor, the remainder should be 0 when we divide this by what it's a factor of. So here we go. Let's test out. I'm just going to start with 1. So a equals 1. And again, what we're really asking is x minus 1 a factor? Right? That's really what we're asking here. So how do I test it out? I'm going to find p of 1 and see if it's 0 or not, because p of 1 is the remainder when I divide by x minus 1. If it is a factor, the remainder should be 0. So here we go. P of 1, I might just drop the color coding here. It'll take a while. So p of 1 equals 2 times 1 cubed minus 5 times 1 squared minus 4 times 1 plus 3. So p of 1 is going to equal 2 minus 5 minus 4 plus 3. So p of 1 is 2 minus 5 is -3, -3 minus 4 is, okay. We can tell this isn't going to equal 0, right? It's going to equal -7, okay? Now, again, we're just testing here. So like if there's one ever where it's like very obvious that it's not going to equal 0, don't feel like you always have to do all the math. Like for sometimes they're just all being added and none of the things are negative, so there's no way it could ever end up being 0. You can kind of just move on and test the next one out. You don't always have to go all the way through, but we can tell this is not going to equal 0. P of 1 does not equal 0. So that means, what does that mean for x minus 1? It's not a factor, right? That is not one of our factors. So see what I mean? It's not guaranteed that all of these a values will give us a factor. It's just that any factor will have one of these. So we're just testing to see which ones, okay? So x minus 1 is not a factor. Whoa, my cat is freaking out. Alrighty, sorry about that, folks. My cat decided to go on a meow fest there. Just paused for a sec. Okay, so p of 1 does not equal 0, so this cannot be a factor, right? If it were a factor, it would have a remainder of 0. So that's okay. We've got other ones to test. Like I said, usually work with the ones and the negative ones first. First of all, those are easier to work with for the math because 1 cubed is still just 1. Second of all, typically we make it so that in the first few you find it, right? We're trying to test your skills, not your endurance to do 100 possible tests. So often it'll be within the first few that you try if you go from lowest to highest. So a equals negative 1. And again, what we're really asking here is, okay, x minus 1 wasn't a factor. Is x plus 1 a factor? So let's see. We're going to test a equal negative 1. How do we test it? We put it in as x in the polynomial and see if the remainder, well, see if the result is 0, because that's telling us what the remainder would be. And if the remainder is 0, it is a factor. So 2 times negative 1 cubed minus 5 times negative 1 squared minus 4 times negative 1 plus 3. What's this going to give me? Well, 2 times negative 1 cubed, that's 2 times negative 1, minus 5 times negative 1 squared. Well, negative 1 squared is positive 1, so this is just 5 times 1. Negative 4 times negative 1, that's positive 4, right? Or 4 times negative 1 is negative 4, and then subtracting that gives us positive 4, plus 3. Okay, this is looking a little more promising. Negative 2 minus 5 plus 4 plus 3. I guess I could have combined those if I wanted, but decided to save it all for the last step here. Negative 2 minus 5. Ooh, look at this. That's negative 7. And then plus 4 plus 3, that's 0. So p of negative 1 is 0. So what did we just learn? We learned that x plus 1 is a factor. Very exciting. So x plus 1 is a factor. That's great. X plus 1 is a factor. Okay, now remember, if I told you that 2 was one of the factors of 6, could you find another factor, even if you didn't know anything about the number 6, right? Yeah, you would say, okay, well, if I divide 6 by 2, that should tell me another factor, right? 6 divided by 2 is 3. Sure enough, that's another factor. Same logic here. We now know one of the factors of this polynomial. So if we divide it by that factor, we should get another factor. So that's what we're going to do next. Call it step 3 if you like. Okay, we're going to find another factor by dividing p of x by this thing that we know is a factor, which is x plus 1. And probably the quickest, easiest way to do that is with synthetic division. So here we go. Our p of x is 2x cubed minus 5x squared minus 4x plus 3. So being on the lookout for the usual, mistakes that students sometimes make, things like forgetting that everything needs to be represented. But in this case, we don't need to put in any zeros because all of the powers of x are represented. X to the third, x to the 2, x to the 1, x to the 0. So we put our a value here, right, for the binomial divisor. For x plus 1, that means our a is negative 1. So the a goes here, the 0, negative 1. And then we just use the coefficients. So the coefficients for p of x are 2 for x cubed, then negative 5 for x squared, then negative 4 for x, then 3 for the constant. And here we go. Time to do synthetic division. So we'll bring down the 2. Then we'll multiply negative 1 by 2 to get negative 2. Then we add down that column. So negative 5 plus negative 2 is negative 7. Negative 1 times negative 7 is going to give us positive 7. Negative 4 plus 7 is going to give us positive 3. And lastly, Here's the moment of truth because we'll be able to check if we've done everything right so far. -1 times 3 is -3. And hey, look at this. 3 plus -3 is 0. That's a good sign because that's our remainder, right? The last thing when we do the synthetic division, that's our remainder. So a remainder of 0 is good because we were supposed to be dividing by a factor. So now we've confirmed, yes, this is a factor. Okay, if we weren't sure before, we're feeling pretty good about it now. And that means my other factor is just whatever this is, right? Well, this represents, again, constant term, then x term, then x squared term. So this would be 2x squared minus 7x plus 3. That's another factor of our p of x. All right. And so now we've got two factors. We're just going to rewrite p of x as a product of what we found so far and then continue factoring as possible. So we're now going to rewrite p of x as a product of these factors and continue factoring. Here we go. Okay, so now we know that p of x is x plus 1. That was one of our factors. And we've worked out that the other factor is 2x squared minus 7x plus 3. I shouldn't say the other factor, but another factor. And now we just need to ask ourselves, okay, can this be factored further? Can we keep going on this? Well, definitely this is just a quadratic. Okay, and we learned how to factor quadratics in Math 10C, and then we did it a whole bunch in Math 20. So yeah, I think we can factor this part further. We can at least try to and see what happens. Okay, now be careful here. We cannot use product sum method because the a value is not 1, right? Remember, this means we need to do decomposition, or sometimes people call it AC method. Okay. They call it AC method because we have to multiply this by this. Again, for reasons that we go over in Math 20. In the interest of time, I might not go too into the details, but if you watch some of the review videos in the agenda or reach out to me, we can talk about the logic behind it. But I'll just run through it here. We need to figure out to factor this by decomposition. So factor by decomposition. Okay, we need to ask ourselves not what multiplies to 3, okay, but what multiplies to 2 times 3, right? So that's our AC. Well, AC is 2 times 3, which is 6. So we have to ask ourselves, what are two numbers that multiply to 6? And it's still what adds to -7. So what multiplies to 6 and adds to -7? How about -6 and -1? Those will work, right? So we're going to take that 2x squared minus 7x plus 3. I'm just going to do it off to the side here because we're just factoring this part. And remember, for decomposition, it's called decomposition because now what we do is we decompose this -7x into 2x terms with these as the coefficients. So we say 2x squared, and I'm going to rewrite -7x as -6x minus 1x, okay? We just have to be super careful here. I'm gonna write it out. And then I'm going to show you why we have to be very careful and maybe rethink what we just did. Remember, for decomposition, our next step is going to be to do this. We're going to factor by grouping for the first two terms and then for the last two terms. So we're going to group those first two and we're going to group those last two. But there's a problem here. I just made a big mistake. Whenever we have a negative right in the middle here, okay, that grouping step actually changes what I'm trying to say. It's not if we have a plus here, we don't have to worry about it. But when there's a subtract here, we can get ourselves in trouble. Because think about what I was saying before. I was saying subtract 1x and then add 3. But just by putting in those brackets, I've changed that. Because now I'm saying subtract 1x and subtract the positive 3, right? I'm subtracting both of these terms in the brackets. So that's why whenever we have a subtraction in the middle there, we need to avoid that before we put in the brackets by changing that minus 1x into a plus negative 1x. It still means the same thing, but it saves us from making that mistake. Because now look, now when I put brackets around it, I'm still saying the same thing I meant to be saying, right? I was never supposed to be subtracting 3, I was supposed to be adding 3. And now I still am. I'm adding a negative 1x, I'm adding a 3, okay? And all we did there, again, we broke that negative 7x, into a negative 6x minus a 1x. That's why we call it that decomposition. So now we can continue. We've grouped the first two, we've grouped the last two, and now we factor each of those groups separately, okay? And in order to do that, we just pull the greatest common factor out of each set of terms, okay? So what's the greatest common factor, the largest thing that's divisible by both 2x squared and 6x? Well, they're both divisible by 2. They're also both divisible by x, right? So our GCF here would be 2x. And then over here, what's the largest thing that's divisible by both negative x and 3? I think just 1. Nothing really, right? I mean, I shouldn't say nothing, but 1. 1 is our greatest common factor. So let's pull the greatest common factor out of each set of terms. I'm going to pull a 2x out of the blue stuff here, the blue grouping. Okay, remember, pulling out a greatest common factor is really just dividing each of these by that thing that they're both divisible by, and then multiplying by it out here. Since we divide each by it and then multiply it by it out here, we don't actually change what it represents. We divided by 2x and multiplied by 2x. But what we do change is we just leave ourselves with something simpler left behind. So I'll have 2x squared divided by 2x. I'm going to divide this by 2x. That's just going to leave me with x, right? 2x squared over 2x is just x. And then negative 6x divided by 2x is just going to be negative 3. So we've got 2x times x minus 3 from the blue stuff. From the yellow stuff here, I'm just going to pull out a 1. And not much is going to happen there. I'm going to divide by negative x, divide by 3. Ooh, okay. Now, remember, to continue on with decomposition, what our next step would be is we should have, if we did it correctly, we should have the same thing left in here as we do in here. Okay, that's kind of a nice way to check our work. Now we're super close, but not quite. I do have an x minus 3 and I have a negative x plus 3. You can see that we're very close to having the same thing. It's just that the sign on each term is wrong. I have x minus 3, positive x, negative 3. And then here I have negative x, positive 3. Whenever that happens, that's just a little clue that, hey, what if you just pulled out a negative 1 instead of pulling out a 1 as the greatest common factor? So that's a little hint to ourselves that, aha, if we pulled out a minus 1, well then, by pulling out a minus 1, negative 1x divided by negative 1 is positive x, and 3 divided by negative 1 is negative 3. And there we go. Now we've checked our work. Well, we can see that the little work check is working. We got the same thing there. That will always happen if we did it correctly for factoring by decomposition. And that's such a crucial step because now, look, it's 2x times x minus 3. Minus 1 times x minus 3. So x minus 3 is a common factor to both things I have here. So I can pull it out of each term. Leaving me with, if I pull an x minus 3 out of the blue stuff here, I'm just left with 2x. And if I pull an x minus 3 out of the yellow stuff here, I'm just left with that negative 1. And there we go. We've now factored 2x squared minus 7x plus 3 using the decomposition methods we learned in Math 20. Okay, if you're a little rusty on that, there are review videos posted in the agenda for those factoring methods. Okay, and again, technically you could have done all this stuff all over again for it, but the Math 20 stuff is a little quicker once we remind ourselves of how it works. Okay, so we've done it. We've now factored this part. We're ready to go. That means p of x fully factored is just going to be x plus 1. That's the factor we found at the very beginning. And now this thing we know factors further into x minus 3 times 2x minus 1. And there you have it. That is the fully factored form. The fully factored form of our polynomial function. Okay, some people would pull that 2 out. We don't actually need to. You could pull that 2 out and leave it as x minus 1/2. It's honestly probably, though, just a little bit easier to leave it like this. It is fully factored. These are the 3 factors, and we could find the x-intercepts and all that from that factored form. We did it. All right, now here's the next one. You can see, in the interest of time here, try to keep this video as not getting too long, okay? I went ahead and did step 1 and 2, because it's always the same, and it really is just testing them out. Here's a quartic, though. They want us to algebraically, and now they want us to actually solve an equation. So factoring is most of the work for that, and then we actually have to use the factored form to find the solutions, just like we did with quadratics in Math 20, okay? But we're going to factor this quartic, okay? Now you can see here, I went ahead and I did the first couple steps, but notice it's the same thing. Find the possible zeros, like what potential a's are we looking for x minus a to be a factor? Well, we look at the constant term. In this case, negative 24. Now that's a little bit annoying because 24 has lots of factors, but again, typically it'll be one of the first few that you try. We're not trying to be too mean with these, and the diploma's not trying to be too mean with them either. But yeah, so the possible things, the possible a values would be the factors of 24. 24 has lots of factors, so I just started testing them, right? Testing a equals 1. I put 1 into our polynomial. It didn't end up equaling 0, so x minus 1 is not a factor. I put negative 1 in to test if a could be negative 1 for a factor. So is x plus 1 a factor? Nope, didn't end up equaling 0, so not a factor. I got lucky on the next one. That's where I finally struck gold. Is 2. Is x minus 2 a factor? I put 2 in to the function, and it did end up equaling 0. So there we go. We now know one factor. We now know that x minus 2 is a factor. So here we go. That moves us into step 2. We can find another factor. So find another factor by dividing p of x by the factor we already know, x minus 2, okay? So we can just use synthetic division. I'm going to make my a value I know is 2. That's supposed to give me a factor. And then for synthetic division, I just use the coefficients. So it's x to the 4th, so I've got a coefficient of, double check to make sure we're not missing anything, but we've got to the power of 4, to the power of 3, to the power of 2, to the power of 1, to the power of 0. Okay. We're good. Remember, if any of those were missing, we would have to include them in our synthetic division still. That's how the algorithm's set up to work. But in this case, we're not missing any, so I don't need to worry about that. So it was x to the 4th, so a 1, negative 5x to the 3rd, positive 2x squared, positive 20x, and then negative 24 was our constant. So I'm going to do synthetic division here to divide that polynomial by the factor x minus 2, and that's guaranteed to give me another factor, right? Dividing something by one of its factors will always give you another factor, if there's another factor to be found. So here we go, synthetic division time. Bring down the 1, get a 1. 2 times 1 is 2. Add them up, negative 5 plus 2 is negative 3. 2 times negative 3 is negative 6. 2 plus negative 6 is negative 4. 2 times negative 4 is negative 8. 20 plus negative 8 is 12. 2 times 12 is 24. Hey, good sign or bad sign? Great sign, right? Negative 24 plus 24 is 0. So my remainder is 0. That's good. That's what it should be if x minus 2 is a factor, which we technically knew x minus 2 is a factor, but it never hurts to get that little confidence boost of seeing, sure enough, the remainder is 0 when we divide our polynomial by x minus 2. Okay, so what does this tell us? It tells us another factor, but what is that other factor? Again, constant x term, x squared term, x cubed term in this case. So that means 1x cubed minus 3x squared minus 4x plus 12 is another factor. Okay, so there we go. We've found two factors already. Now, whoops, I guess that was step 3, sorry. Step 4 is rewrite this as a product of its factors and continue factoring. So here we go, okay? We now know that p of x can be rewritten as a multiplication of x minus 2 by that other factor we just found. So that was x cubed minus 3x squared minus 4x plus 12. And so now we've got to look and see, can this still be factored? Can this still be factored? And here's the thing. It could. It can. Okay. Now, what we can do, what we sometimes have to do is, this is a cubic, right? It's not a quadratic, so you couldn't use your Math 20 stuff on it yet. Okay. So what we often will have to do here is now go back to step 1 and with just this thing, right? Basically, I mean, this is a polynomial. We can factor it using this process. So we could take this, go back to step 1 and work through it again. Okay, and then we should end up with a quadratic and be good to go. Okay, in this case, I'm just going to try something because sometimes this works with cubics. It often won't work with cubics, but I'm just going to try something. So we could restart process. I shouldn't say restart. It's not like we're restarting, but could redo this process here. Could redo the process with this. But do you remember this? This sometimes works. It's basically like decomposition, except we're not doing the decomposition part. It's like the last couple steps of decomposition. It's factoring by grouping. It works when you have 4 terms. Okay, which we do have 4 terms here. It is kind of worth a shot to at least check when you have like a cubic here with 4 terms. It's worth a shot to see if you can factor by grouping, because factoring by grouping is pretty quick, but not always going to work out, okay? It does end up working out here. I'll show you one where it doesn't end up working out, and we do have to go back to the beginning. So p of x, well, here, let's just see. Let's see if we can factor this by grouping. So it is really, like I said, it's just like the finish of factoring by decomposition. Notice we have 4 terms. Maybe we can do this. Maybe we can group and group, except be careful. Notice that minus there. Okay, we're getting unlucky today. There's always the minus so far for us today. I'm going to rewrite this as plus minus 4x. I'm going to rewrite it as plus negative 4x. Just so that I don't change the meaning when I group these. Don't want to change the meaning when I group them. There we go. Now it does end up working here because look, the greatest common factor of this stuff is x squared. This is divisible by x squared, so is this. So if I pull out x squared as the GCF, the greatest common factor, I end up with, well, x cubed divided by x squared is x. Negative 3x squared divided by x squared is negative 3. And then here, look, if I pull out negative 4 as a greatest common factor from this stuff, from this group, negative 4x divided by negative 4 is just x, and 12 divided by 4 is negative 3. So this case, it worked out. Again, this is not always going to happen with these cubics with 4 terms, but that's what I meant by will it work out or not. Will we end up with something common from our 2 groups that we can then pull out as a common factor and just be left with 2 factors? In this case, it did actually work out. X minus 3 is in both of these groups here, right? I have x squared times x minus 3 minus 4 times x minus 3. They're both being multiplied by x minus 3, so it is a common factor. So if I pull that out of the blue group there, I'll end up with x squared And from the yellow group, I'll end up with a minus 4. Ooh, I probably shouldn't use blue. I used blue for p of x. Whoopsies. I should have used a different color. Sorry. But hey, we did it. This has now been factored. Okay, so we factored that polynomial, that x cubed minus 3x squared minus 4x plus 12. Let's rewrite what we know now. So now we know p of x is equal to x minus 2 times all that stuff, but we factored that into this. We factored by grouping. Okay, and we're almost done, but I actually see even more factoring we can do. Can we factor x squared minus 4? Do you remember special polynomials? This is actually a difference of squares. Now, we could actually treat it like a trinomial with an x term of 0 and use product sum method. That would actually work still. But differences of squares are super fast to factor because, again, a difference of squares is, well, it's a difference of squares. It comes from the fact that if I have, let's say, a plus, I'll say x plus a times x minus a. Again, a could be whatever we want. So if I show something here, it means it works for any number. A is standing in for any number. If I multiply that out, x times x is x squared, x times negative a is negative ax, a times x is positive ax, and a times negative a is negative a squared. Well, negative ax plus ax is just 0, so it always multiplies out to be x squared minus a squared. So this is a difference meaning subtraction, of squares, meaning perfect squares. Whenever I have a perfect square minus another perfect square, it's always going to factor into multiplication of their conjugates, meaning x plus, like the x plus a times x minus a. That's the conjugate part. X minus a is the conjugate of x plus a. Okay, so whenever I have this, it's just the square root of the first plus the square root of the second times the square root of the first minus the square root of the second. That's how we factor a difference of squares. So this actually just ends up equaling x minus 2, here I'll point it out, difference of squares, okay, x minus 2 times x minus 3 times, using difference of squares here, this is going to be x plus 2, right? Square root of x plus the square root of 4 times x minus 2. Square root of x minus the square root of 4. And there we go. We did it as we would predict, 4 factors in the end, because it was a quartic to start with, right? Our degree on x was to the power of 4. Now, we fully factored it, but don't forget, I know especially these ones that take a little while to do, don't forget to actually make sure you've answered the question. We weren't just trying to factor it, we were actually trying to solve it algebraically. It was an equation that we were trying to solve. So we weren't just trying to write the factors, we were trying to find the values of x that make it true. Why factor then? Well, again, do you know what number, when I put it to the power of 4 and I subtract 5 times it cubed plus 2 times it squared plus 20 times it minus 24 will equal 0? Me neither. I'm a math teacher. I had no idea what numbers do that, okay? But what I do know is how to make this equal 0, right? And this equals 0, and this equals 0, and this equals 0. Make x 2, make x 3, make x negative 2, make x 2. That is why factoring is so powerful. Same reason it was so powerful in Math 20. It allows us to very easily see, once we've factored this thing, we can very easily see what values of x would make this equation true. So now we're actually going to find our solutions. Don't forget, we started this all out by saying we wanted to figure out when is x to the power of 4 minus 5x cubed plus 2x squared plus 20x minus 24, when is that equal to 0, right? And what we've now figured out is that this p of x is actually just equivalent to x minus 2 times x minus 3 times x plus 2 times x minus 2. And that equals 0. okay? And we're being asked what x's could make that true. Well, I'm just multiplying 4 things together, and apparently the answer is 0. So that's only possible when they are 0 themselves, right? Any value of x that makes any of these factors 0 will make this equation true, because 0 times anything is 0. And so now it becomes pretty quick to pick out that, okay, this would be 0 if x minus 2 equals 0, obviously. So if x equals 2. This one, if x minus 3 equals 0. So if x equals 3. This one, if x plus 2 equals 0. So subtract 2 from both sides if x equals negative 2. And this one, if x minus, how do we make x minus 2 equal 0? Well, add 2 to both sides. We could make x equal 2. So the solutions are x equals 2. I guess this is just a repeat. 2 shows up twice. 2, 3, or negative 2. And there we go. We solved this algebraically by factoring. Pretty cool, huh? Okay, so I did just really want to quickly show you as well. This one, again, it's worth a shot to see if you can factor by grouping. Sometimes it's not going to work out, though. Sometimes this isn't going to happen where you end up with the same thing, so you can pull it out and get a nice factor like that. Always worth a shot because it is a pretty quick, nice, easy way to do it. I did just want to show you, I'm not going to fully go through the example. It's one from your assignment, and you can check my solution, you know, in the filled in notes and look at it a little bit more slowly without me scrolling through and talking over it. But I just want to show you what happens when you can't do that. And you just recycle. You do the whole thing again, but for that factor. So here we factored this quartic function, okay, or expression, I guess it's not listed as a function there. Same thing, find the possible a values, test them out. You find one factor, found that x plus 1 is a factor. So I found another factor by dividing what I started with by x plus 1 using synthetic division. That gave me another factor. And notice here, this factor, this one's not going to work out. If I group these, I'm not going to end up with the same thing, okay? So what do? I now take this, hey, what we just learned was how to factor polynomials with a degree greater than 2. What is this? It's a polynomial with a degree greater than 2. So I write it out, rewrite it, and now I'm going to have to repeat the process for this, right? So look, I go back to step 1. I list out the possible factors for this, or the possible zeros for this, right? Same, it's happened to be 24 again, okay? So then I go through, I test these out now. Test these out. Had to test a few, had to test quite a few. Finally got it when x was negative 2, okay? Telling me that x plus 2 is a factor of this thing, right? The thing I'm trying to keep factoring to continue factoring the quartic we started with. And now notice, I'm just repeating the steps, right? So take this now, divide it by x plus 2 using synthetic division. That gives me another factor, okay? And now I can say that this, right, the other factor I got was this quadratic here. So this cubic that we got after our first round of doing this whole process is just x plus 2. We found that back here, right, by doing step 1 and then synthetic division to get the quadratic, okay? And now we're at the stage, whenever you get finally a quadratic showing up, now you can definitely just use your Math 20 skills and get something like this, okay? Use product sum or something along those lines. And then we've finally fully factored this one. X plus 1, x plus 2 times x plus 4, x minus 3. Just factored that with product sum. So just showing you, if you get a cubic after your first round of doing it, that's okay. You now just repeat the process for that cubic. But again, worth checking if it can be factored by grouping, because that's a little bit quicker, I'll be honest. Okay, so just all that's here is a little summary of the process, okay, everything we just talked about. To factor a polynomial p of x, list the potential zeros, right? The possible a values for x minus a to be a factor by finding the factors of the constant term. That narrows down your search. Then you've got to test them. So test the potential zeros by substituting the possible a's into p of x as x. If x is minus a is a factor, then p of a will be 0 by the remainder theorem / the factor theorem, right? Really They're kind of inseparable when we use them in this context because we're using the fact that P of A is the remainder, and then the factor theorem tells us that P of any A that's part of a factor will be 0. The remainder will be 0. Okay? Once you've got a factor, x minus A, use synthetic division to find another factor, and then repeat as necessary with the quotient until the remaining factor is a quadratic that can be factored using your Math 20 skills. All right, all that's left here is one diploma example, one from a release diploma, and then we are done. All right, so one from a diploma, let's do it. In order to factor the polynomial function p of x equals 3x cubed minus 2x squared minus 19x minus 6, a student determined that the function has a 0 of x equals 3. Okay, that's very important. That's very interesting because that already tells us about what one of the factors must be. He then wrote the polynomial as a product of a linear factor, so that just means an x. It's just got an x as the highest power, well, x to the power of 1 is the highest exponent on x, and a quadratic factor, as shown below, where a, b, and c are elements of the integers. So it's just letting us know that a, b, and c are all integers. They're not like decimals or weird fractions or anything like that. Okay, well, let's think about this. If the function has a 0 of x equals 3, what that means is making x 3 makes the function equal 0, right? So what factor does that tell us exists for this function? Well, if x equals 3 is a 0, then x minus 3 is a factor, right? If making x 3 is going to result in a 0, then that tells us x minus 3 must be one of the factors. And then we'd have 0 times another factor giving us the function 0. Okay, so right off the bat, we can actually eliminate two options here. They're telling us that p of x can be written as x plus a, and then they're asking us what a would be. Okay, well, this factor is obviously not this quadratic one here, right? That's the other one. This is the one that looks like x minus 3. So what is a? X plus what would be x minus 3? X plus negative 3. So it's one of these. It's either a or b. Right off the bat, we've eliminated c and d. Okay, if negative 3 were a 0, then I agree. If x equals negative 3 were a 0, then we could say x plus 3 were a factor, right? But not in this case. Okay, so that just means, again, that means, right, what we said here is p of x equals x minus 3. If x minus 3 is a factor, we can write it as x minus 3 times another factor. Right? So that is the a part. Okay, now we just need to find the other factor because we know this is the other factor part, right? That's this part, but we want to figure out what b is. So now we just need to find the other factor, find other factor, to determine b. To determine b. Okay, this is what we're looking for. What is that? We know it's some quadratic factor, but what is that b? Well, once again, we have one factor. Okay, we have one factor. We know p of x. Again, if I told you 2 is one of the factors of 6, how could you find another factor? We'll divide 6 by 2 to find 3, right? 2 times 3 equals 6. 2 and 3 are factors of 6. So 6 divided by 2 is 3, the other factor. If you know 2, then 3 must be a factor too. So same idea here. We know one factor of this polynomial. Let's divide by that factor to find another factor. So I'm going to use synthetic division. Our a is our a is positive 3. Sorry, our 0 is 3. Got myself mixed up there because I was looking at this and it was saying x plus a, but I was forgetting that we know the 0 is x equals 3. We know the factor is x minus 3. So the a value there, the 0 of the function is 3 for our factor here. And then just using the coefficients, 3, negative 2, negative 19, negative 6. 3, negative 2, negative 19, negative 6. And here we go. Bring down the 3. 3 times 3 is 9. Add down that column. Negative 2 plus 9 is 7. 7. 3 times 7 is 21. Negative 19 plus 21 is 2. And then lastly, 3 times 2 is 6. Hey, very good sign. Negative 6 plus 6 is 0. That's exactly what we would expect. And now we feel even better about saying that x minus 3 was the factor, and therefore that a must be negative 3. Okay, and here we go. What is this other factor then? Well, constant, then x term, then x squared term. So this is 3x squared plus 7x plus 2. So what is b comparing to this? What is b? 3x squared plus 7x plus 2. So b is 7. They didn't ask us for c, but now we know that c is 2. Fun fact. So b is 7. So the answer overall here must be option B. A is negative 3 and B is 7. Just using our factoring skills. It's kind of fun. I find it very satisfying to factor these all the way down. Okay, go ahead and try these out using those strategies we just talked about, and then that's it for this lesson. So you can do the rest of the practice for this as well. Anything you've left for after the lesson, you can work on for, well, as much as you need. Okay. As always, don't be shy to reach out with questions, concerns, book a meeting with me, and all that stuff. All right.